Welcome you all to this lecture. In this lecture, we are going to see the different types of noises and how to generate a noise in a communication system. A noise is defined as an unwanted signal which tends to interfere with the modulating signal, which means a message signal. So it is basically divided into external noise and internal noise. Now we'll see the subclassification of these two noises. External noise is again divided into atmospheric noise, extraterrestrial noise, and industrial noise. The internal noise is again divided into thermal noise and sound noise. Now we'll see the definition and explanation of these classification of noises. First one is external noise. In that, atmospheric noise is defined as a radio noise caused by natural atmospheric processes, primarily lightning discharges in thunderstorms. And extraterrestrial noise is the radio disturbances from sources other than those related to the earth. General examples for extraterrestrial noise are cosmic noise and solar noise. Cosmic noise is the random noise that originates outside the earth's atmosphere, and solar noise is the noise that originates from the sun. It is called as solar noise. The another classification in external noise is industrial noise. It is the noise generated by automobile ignition, aircrafts, electric motors, switchgears, welding, etc. Now we'll see the internal noise. The internal noise is classified as short noise and thermal noise. The short noise is defined as the random motion of electrons in the semiconductor device that generates the short noise. And thermal noise is also known as Johnson noise. It is the random motion of electrons in the resistor that is called as thermal noise. It is generally expressed as Vn equal to Kt0Br, where K is the Boltzmann constant, R is the resistance, T0 is the absolute temperature, and B is the bandwidth. Now we'll see the noise calculation. For noise calculation, we need to understand the terms noise temperature and noise figure. The noise temperature means for specifying noise in terms of an equivalent temperature. It is generally expressed as T equal to Fn minus 1 into C0, where Fn is the noise figure and T0 is the noise absolute temperature. We see the basic definition and expression of a noise figure. It is the ratio of output noise to input noise of an amplifier or network. It is generally expressed as Fn equal to Kt0Bg plus del n divided by Kt0Bg, where del n is the noise added by the network or amplifier. G is the gain of the network or amplifier. This is an example calculation of noise figure for a cascade amplifier. So a cascade amplifier is the a series connection of number of stages of amplifier. So where each stage will be consisting of a noise figure and gain. So it can be expressed as Fn equal to F1 plus F2 minus 1 divided by G1 plus F3 minus 1 divided by G1 G2 plus etc. So each stage will be consisting of a noise figure and gain. Before proceeding with noise calculation, we see the concept of noise equivalent bandwidth. So generally a noise is added to the generated modulated wave. So that added noise is generally treated as a white noise. So white noise is divided as a flat spectrum of frequencies which will look like a white light. It is passed through a filter which is having some frequency response. So that frequency response is nothing but a filter. Through that filter, if you pass some white noise, some of the noise power will be rejected and some of the noise power will be passed through the filter to the output. This is the noise equivalent bandwidth with picture representation, where in x-axis we are having frequency and in y-axis we are having modulus of h of f of square. So we'll be having a bandwidth range from minus bn to bn, where bn is the bandwidth of the noise. So this range of minus bn to bn is we call it as a noise equivalent bandwidth. So this is the figure of merit definition with respect to SNR. SNR is the signal to noise ratio, where S stands for signal and N stands for noise. So if you take the ratio of S to N, that is called, generally called as a signal to noise ratio. So here fear of merit is expressed in terms of SNR of output and SNR of input of a communication system, where S0 is the output signal power and N0 is the output noise power and SA is the input signal power and NA is the input noise power. Now we will move on to the receiver model for noise calculation. That is our main objective of this lecture. So this is a generalized diagram. Just have a look of this. So in this we are having a modulated signal, that is S of t, a channel that is N into W of t, which is given to a summation block, and a band pass filter and a demodulator. So this is called as a receiver. So now we compare this block with this block diagram. So the same block is represented like this. Here we are having three different sections. The very first section is transmitter, and the intermediate section is channel, and the last section is receiver. The transmitter section will be generating the modulated wave with the help of modulator, and in the receiver section we are getting the demodulated wave, which is actually we are using for noise calculation. And the intermediate we are having a channel which is used to add the noise to the modulated wave. Now we can take the message signal as a M of t and carry signal as C of t. The modulated signal we generally represent it as a S of t. So along with this S of t, we'll be adding a noise, that is eta W of t, where W represents the white and N represents the noise. So N W of t or eta W of t, the white noise that we are adding to the modulated signal S of t. That will be given to the band pass filter. The band pass filter filters the sum of the noise and passes the sum of the noise to the output. So we have to calculate the passed noise at the output of the demodulator. So the band pass filter output is given as y of t equal to s of t plus n b of t, that is band pass noise. Previously we have represented as white noise nw of t. Now this is given to the demodulator block, and finally we will be getting the n0 output noise. So this is a general system that we calculate for noise of a communication system. Now we see the spectral density for this noise calculation. So this is the power spectral density of a white noise. So in the x-axis we are having frequency, and the noise power spectral density is given for a magnitude n0 divided by 2. Where P is equal to N0 into B. N0 is the noise and B is the bandwidth of the noise. So we have calculated the power spectral density, and we have seen the block diagram to calculate the noise of the communication system. So this band pass noise that we are getting at the output of the band pass filter can be represented in two domains, that is time domain and frequency domain. In time domain we can have quadrature and envelope representation, and frequency domain we can have only frequency representation. In quadrature representation, the noise can be represented as in phase and quadrature component, where NI of t is the in phase component of a low pass noise and NP of t is the out phase or a quadrature component of the low pass noise. So this is a general block that we will use to understand the quadrature or in phase representation of a band pass noise, that is getting out the output of the band pass filter, which is given to the product modulator. In the product modulator we are generating in phase component sin omega ct and quadrature component cos omega ct, that is given to the band pass filter to obtain my final in phase and quadrature noise output. And finally, this is the frequency domain representation. In frequency domain representation, we are representing the NB of f, that is band pass noise in frequency domain, with a bandwidth of 2B. So that's all about the noise calculation and noise representation of the communication system. Thank you.